Well, hello everybody, and happy virtual learning day. On this extremely cold day, I thought it was appropriate to throw in a selfie I took while hiking out in Arizona on New Year's Day. It was a whole lot warmer then than it is in Iowa today. The topic we're going to be looking at is called end behavior, and it basically involves the idea of infinity. What we're basically looking at is what happens at the right side of your paper when you make a graph. What's the end behavior of your graph? So as x gets bigger and bigger and bigger as it goes toward infinity, what's happening with the y's? So this is what the notation for end behavior looks like. And what you would most likely do looking at this to read it aloud is to say the limit as x goes to infinity of f of x. That's what pretty much every calculus student has ever done, myself included. Although I will tell you some professors can get really huffy about saying x goes to infinity. Because of course infinity isn't really a number, it's bigger than every number. And some professors would want you to say something like the limit as x gets very large, or the limit as x increases without bound. You can say x goes to infinity in my class, but do realize those other things mean the same thing. So what we want to figure out today is exactly what can happen over at the right side of your graph. What are the possibilities when x gets very large and goes toward infinity? For the most part, there are three things we're going to look at. One of the most common is that you'll have an answer of 0. And if you look at these graphs, you can see what's happening is over at the right side of your paper, the graph is getting very close to the x-axis. So it's getting close to where y would be 0. Another possibility is that we could say the limit as x goes to infinity is 1. Or it could be some other number besides 1. Here, what's going to happen is you'll have an asymptote. You'll have a line that you get close to over at the right side of your graph, but that line is something other than the x-axis. And the final possibility is you could say that the limit ends up being infinity, or sometimes we'll say instead negative infinity. Here, what's going to happen is that if you go to the end of the graph, it just keeps getting higher and higher, or if it was negative infinity, it would keep getting lower and lower. It goes up forever. You remember graphing parabolas, and that has a limit as x goes to infinity of infinity. The vast majority of problems you're going to see will give you the equation for a function, and it's going to ask you what the limit as x goes to infinity is. The time we care about that almost always is when we have what's called a rational function. That means you have a function that's a fraction. Like here I have x squared plus 3x minus 2 all over x cubed minus 5x squared plus 7x plus 11. If you think of most of the problems that have come up on the worksheets we've done recently, those have all been rational functions, and if you graph them, they could do any of the things we just talked about at the end. What we want to do is figure out whether the limit is 0, 1, or infinity. And to do that, what a book would tell you to do is to compare the degree of the numerator and the degree of the denominator. So all that means is you look at the biggest exponent on top and the biggest exponent on the bottom. In this problem, the numbers I care about are the 2 from x squared on top and the 3 from x to the third on the bottom. I'm going to compare 2 and 3. So I look at those two exponents, and what I care about is which one's bigger. Here it tells you if I have a rational function, and the top is less than the bottom, like 2 is less than 3. Again, we're just looking at those exponents on the biggest term. Then I'm going to have a limit of 0. So the limit of this whole big function is 0. That's even true if you have other big numbers that come up in the problem. Here I've got things like 1,000 and 1,000,000 on top, but they're really not going to affect our answer. What I care about is that the big exponent on top is 9, the big exponent on the bottom is 10, and 9 is less than 10. And if the degree of the numerator is less than the degree of the denominator, my answer has to be 0. So what's probably going through some people's mind is why? And it's actually not that hard to figure this out. If you take a big number to the 9th power, you're going to get a big answer. But if you take a big number to the 10th power, you're going to get an enormous answer. And by the time you've taken something to the 10th power, even if I've got a smaller number and I multiply by 100, that number that's to the 10th power is still bigger. Things like multiplying by 100 or adding 1,000,000 don't make a lot of difference if you've got hundreds of zeros after your number already. So it's that exponent that really makes the difference in how big things are. Here, we'd have a fraction that has a bigger number on the bottom than it does on the top, like 2/7. Well, that's a small fraction, and as you make that bigger and bigger on the bottom, it's going to get closer and closer to 0. So the first big thing to remember is look at the biggest exponent, top and bottom. If the top's less than the bottom, your limit is 0. The second rule is kind of the opposite. It says any rational function where the top is bigger than the bottom will have a limit of infinity. Here I've got x squared plus 3x plus 2 over 12x minus 13. What I care about is it's x squared on top and it's x to the first on the bottom. 2 is bigger than 1, top's bigger than the bottom, so it's going to go to infinity. The idea here is I have fractions where the number on top is bigger than the number on the bottom. It's like bigger than 1 overall. And if you take that to bigger and bigger powers, it's just going to keep getting bigger. There's also some easier functions that have limits of infinity. Like if you graph a parabola like x squared, it's just going to keep going up forever. And the same's true if you graph a line like y equals 5x. So if it just keeps going up, you've got a limit of infinity. I said earlier that you could get negative infinity as a limit. The way that happens is if you have a negative coefficient on that term with the biggest exponent. So like in this problem, I've got negative 5x to the 7th plus 4 all over 3x to the 5th minus 6x plus 2. The fact that 7 is bigger than 5 tells me this is going to be infinity, and the fact that it's negative on that term on top tells me it's going to be negative infinity. Now, this is not the function that's graphed in the picture, but the idea of a limit of negative infinity is it's going to go down to the bottom when you go to the end of the graph. So again, what you care about is compare the biggest exponents top and bottom. If the top's bigger than the bottom, your limit is infinity. And the third and final rule is that if you have a rational function where the biggest degree on top is equal to the biggest degree on the bottom, you're going to have a limit of 1. In this function, the biggest exponent on top is 2, the biggest exponent on the bottom is 2, and so my limit is 1. Have a little bit of an idea here of what's going on. Here I plugged the numbers 20 and 70 into that function. And I just got out a calculator and I squared, I added 3 times the number, I added 2, and then I divided by all the stuff on the bottom. I did that for 20, and you notice that I got like 0.83695. When I plugged in 70, I got 0.9463. So you notice it's getting bigger and it's getting closer to 1. Now, I didn't want to take the time or space to plug in like 100 or a million or a billion, but what happens when you start plugging in really big numbers is, again, all that stuff at the end, like 3x plus 2 and 7x plus 12, doesn't really affect your answer very much. And you're going to get closer and closer to having the same thing top and bottom. That's why we end up getting a limit of 1. Now, I said you could get a limit of some number, and I said it was usually 1, but it could be some other number. The way you get a number that's not 1 is you have a coefficient by the biggest exponent. So I have an example here where there's a 2x squared on top, and on this one, my limit's going to be 2. And here's 2 other examples, and they're both here to make a couple of points. If you look at the top one, you'll notice that the biggest exponent, top and bottom, is 7. But the bottom's written backwards, and it's telling you there that you need to be careful what you look at. If I look at the coefficients, I've got 5x to the 7th and 9x to the 7th, and that's why the limit on this one is going to be 5/9. On the bottom one, you can see I put the limit was 16. Well, I know it's going to be a number because we got squared, top and bottom. And what I did here is I took 4 squared to get that 16. Usually, when your exponents are the same, you're going to have a limit of 1, but the weird stuff happens when there's numbers in front. Again, though, the main thing you want to remember is look at that biggest exponent, and if they're equal, the top equals the bottom, then usually your limit is 1. So summing it up, if the top's less than the bottom, your limit's 0. If the top equals the bottom, your limit's 1. And if the top's greater than the bottom, the limit is infinity. So I'm going to throw one other possibility at you today. Every once in a while, you might encounter some really weird function that has no limit. Probably the simplest function like that is f of x equals sine x. We would say this has no limit, and the reason why is that it just keeps bouncing up and down over and over again, so it's not going to any specific number, and it's also not getting bigger and bigger forever. And because of that, the limit doesn't exist, or it has no limit. Again, though, what you really want to drill into your head is look at those exponents in the fraction. Biggest exponent on top, the biggest exponent on the bottom. If the top's less, it's 0. If they're equal, it's 1. And if the top's bigger, it's going to be infinity. And that's what we're learning in this next section. We'll come back and do some problems with those Monday and go on from there.